Vibration analysis, understanding and managing complex vibration in machinery, techniques to analyze and control machine vibrations. Definition and examples of complex vibration. Complex vibration refers to the phenomenon where multiple vibration sources combine to produce a waveform that is intricate and difficult to interpret in the time domain. Unlike simple vibration, which can be represented by a single sine wave with a clear amplitude and frequency, complex vibration results from the superposition of several sine waves originating from different components of a machine. For example, consider two masses on springs oscillating independently. Each generates its own sine wave. When these waves are combined, the resulting waveform becomes irregular and visually confusing. In real-world machinery, this complexity is amplified because machines consist of numerous components such as rotors, shafts, bearings, gears, and fan blades, each contributing vibrations at distinct frequencies and amplitudes. These combined vibrations create a composite signal that cannot be easily analyzed by observing the time waveform alone. This complexity poses challenges for maintenance and fault diagnosis because the waveform does not reveal which component is responsible for a specific vibration pattern. Therefore, understanding complex vibration is essential for accurate machine condition monitoring and predictive maintenance. Analysts must recognize that the time domain representation of vibration is insufficient for diagnosing faults in machines with multiple interacting components. Instead, advanced techniques such as frequency domain analysis are required to separate and identify individual vibration sources. This foundational concept sets the stage for exploring how complex vibration manifests in machines and why specialized tools are necessary to manage it effectively. How complex vibration arises in machinery. In machinery, complex vibration arises from the interaction of multiple components operating simultaneously, each generating its own vibration signature. A typical machine includes rotating shafts, couplings, bearings, gears, and sometimes fans or impellers. Each of these elements introduces forces that vary in magnitude and frequency, resulting in a composite vibration signal. For instance, the rotor may produce a vibration at the shaft rotational speed, while bearings generate vibrations at characteristic defect frequencies, and gears contribute harmonics related to gear mesh frequencies. When these signals combine, the resulting waveform becomes highly complex, making it difficult to isolate individual sources by visual inspection of the time domain data. This complexity is further influenced by factors such as load variations, misalignment, and structural resonances, which can introduce additional frequencies and modulations. The combined effect of these sources creates a vibration pattern that reflects the overall dynamic behavior of the machine rather than the condition of a single component. Consequently, diagnosing faults requires separating these overlapping signals to identify their origins. This is why vibration analysts rely on spectral analysis, which transforms the time domain waveform into a frequency domain representation, allowing each component's vibration to be displayed as distinct peaks corresponding to its forcing frequency. Understanding how complex vibration develops in machines is critical for implementing effective monitoring strategies and ensuring reliable operation. Fan vibration, blade pass and shaft vibrations in fans. Fans provide an excellent example of complex vibration because they incorporate multiple vibration sources within a single assembly. The primary source is the shaft rotation, which generates a vibration at the running speed or 1x or 1 order frequency. If the fan is imbalanced, this vibration becomes more pronounced. Additionally, the fan blades introduce another source of vibration known as blade pass frequency. This occurs because each blade interacts with the surrounding air or structural elements once per revolution, creating periodic impacts. The blade pass frequency is calculated by multiplying the number of blades by the shaft rotational speed. For example, a fan with 8 blades rotating at 10 revolutions per second will produce a blade pass frequency of 80 Hz. When these two sources, shaft rotation and blade pass, combine, the resulting waveform becomes complex and difficult to interpret in the time domain. If additional factors such as bearing defects or aerodynamic turbulence are present, the complexity increases further. In practice, analysts use spectral analysis to separate these components. In the frequency domain, the shaft rotation appears as a peak at 1x or 1 order, while the blade pass frequency appears as a peak at a higher multiple of the shaft speed. This separation enables accurate identification of issues such as imbalance, blade damage, or aerodynamic problems. Understanding fan vibration is crucial because fans are common in industrial settings, and their failure can lead to significant downtime and maintenance costs. By recognizing the distinct vibration sources in fans, analysts can apply targeted corrective actions, such as balancing the rotor or repairing damaged blades, to restore optimal performance. How complex vibration relates to a machine. In real-world machines, vibration is rarely simple. Machines consist of multiple moving parts, each potentially contributing to the overall vibration signature. Complex vibration in a machine can arise from rotating components, shafts, gears, fans. Imbalances, mass not evenly distributed. Misalignments, shafts not aligned properly. Looseness, mechanical parts not tightly fastened. Resonance, natural frequency matches excitation frequency. Bearing faults or gear defects. These sources combine to create a complex vibration signal that must be analyzed to diagnose machine health. Here's a waveform diagram illustrating how multiple machine components contribute to a complex vibration signal. Let's explore the breakdown of the plot. Each subplot shows the vibration from a different machine component. Number 1, rotor, 30 Hz, a strong, low-frequency oscillation. Number 2, pulleys, 60 Hz, higher frequency, moderate amplitude. Number 3, gears, 90 Hz, even higher frequency, smaller amplitude. Number 4, bearings, 150 Hz, high frequency, low amplitude vibration. Number 5, fan blades, 45 Hz, mid-frequency, moderate amplitude. Number 6, combined signal, the sum of all the above, forming a complex waveform. Key insight we can take from these are: even though each component vibrates in a simple, predictable way, their superposition creates a waveform that looks irregular and complex. This is what makes vibration analysis both powerful and challenging in real-world machinery. Here's the frequency spectrum, FFT, of the complex vibration signal. What this shows. Each peak in the spectrum corresponds to a specific machine component. Rotor at 30 Hz. Fan blades at 45 Hz. Pulleys at 60 Hz. Gears at 90 Hz. Bearings at 150 Hz. Why this matters? This is how vibration analysts identify which components are contributing to the overall vibration. By comparing the measured spectrum to known component frequencies, you can diagnose faults like imbalance, misalignment, or bearing wear. Here's the waveform diagram illustrating the vibration from a fan shaft and fan blades hitting a piece of paper. Breakdown of the diagram. Number 1, top plot, shaft vibration, 10 Hz. Represents the low-frequency oscillation due to the rotating shaft. Smooth and periodic. Number 2, middle plot, blade hit vibration, 40 Hz. Each of the 4 blades hits the paper once per shaft rotation, 4 hits per rotation times 10 rotations/SEC equals 40 Hz. Higher frequency, sharper oscillations. Number 3, bottom plot, combined vibration. The sum of the two signals appears complex and irregular, even though it's just 2 sine waves added together. Key insight we can take. If you only had the combined waveform, it would be very difficult to tell that it came from a shaft and fan blades without knowing the system. This is why frequency analysis, like FFT, is essential in vibration diagnostics. Here's the frequency spectrum, FFT, of the combined vibration signal from the fan shaft and fan blades. How to interpret this spectrum? Number 1, 2 clear peaks. 10 Hz, this is the shaft rotation frequency. It represents the fundamental vibration due to the rotating shaft. 40 Hz, This is the blade pass frequency, for blades times 10 rotations per SEC. It represents the periodic impacts as each blade passes a fixed point, like hitting a piece of paper. Number 2, amplitude differences. The shaft vibration has a higher amplitude because it's a stronger, more dominant motion. The blade vibration has a smaller amplitude, but it's still clearly visible in the spectrum. Number 3, why this matters. If you only looked at the time domain waveform, the signal would appear complex and hard to interpret. But in the frequency domain, you can clearly identify the individual sources of vibration. This is the power of FFT in vibration analysis. It transforms a confusing waveform into a readable signature of machine behavior. Dealing with complex vibration, spectrum analysis, and advanced techniques. Managing complex vibration requires moving beyond time domain analysis to frequency domain techniques such as spectrum analysis. The fast Fourier transform, FFT, is the primary tool used to convert a time waveform into a spectrum, which displays vibration amplitude as a function of frequency. This transformation allows analysts to separate overlapping signals and identify individual vibration sources. For example, in a fan system, the shaft rotation and blade pass frequencies appear as distinct peaks in the spectrum, making it possible to diagnose imbalance or blade-related issues. Spectrum analysis also reveals harmonics, sidebands, and other patterns that indicate specific fault conditions such as misalignment, gear defects, or bearing wear. In addition to FFT, techniques like order analysis, which expresses frequencies as multiples of running speed, simplify the interpretation of spectra for variable speed machines. Advanced methods such as envelope analysis and demodulation are used to detect early-stage bearing faults by isolating high-frequency impacts. Analysts may also employ time-synchronous averaging to reduce noise and highlight periodic signals. The key advantage of these techniques is their ability to provide clear, actionable insights into machine health, even when the vibration signal is highly complex. Implementing these methods requires proper data acquisition settings, including appropriate sampling rates, resolution, and filtering, to ensure accurate results. By leveraging frequency domain analysis and related tools, maintenance teams can overcome the challenges posed by complex vibration, enabling proactive fault detection and minimizing unplanned downtime. How to deal with complex vibration. Dealing with complex vibration involves several steps. Number 1, measurement. Use vibration sensors like accelerometers, velocity transducers, displacement probes. These sensors collect time domain data which can be transformed into frequency domain data using fast Fourier transform, FFT. Number 2, analysis. Spectral analysis, identify dominant frequencies and their amplitudes. Order analysis. Useful for rotating machinery to correlate vibration with rotational speed. Time waveform analysis, helps detect transient events like impacts or looseness. Envelope analysis, useful for detecting bearing faults. Number 3, diagnosis. Match the identified frequencies with known fault frequencies. Unbalance 1 times RPM. Misalignment 1 times and 2 times RPM. Bearing faults high-frequency components. Gear mesh frequency and sidebands. Number 4, correction. Balancing. Add or remove mass to correct unbalance. Alignment, use laser alignment tools. Tightening, secure loose components. Isolation, use vibration isolators or dampers. Maintenance, replace worn bearings, gears, or blades. Number 5, monitoring. Implement condition-based monitoring, CBM, or predictive maintenance, PDM, using continuous vibration monitoring systems.